Okay, thank you. So today I want to talk about a fairly new thing in Idris. I want to talk about how we deal with side effects. Obviously, we have a pure functional programming language. We have to have some way of dealing with effects. And of course, those of you who are familiar with Haskell will think effects. Well, that's obviously monads. And what I'm going to talk about today arose from me just suddenly getting fed up with monad transformers quite a lot. So what we're going to do is look at how to write an evaluator for a simple expression language. So the kind of thing we did on Tuesday, looking at writing down expressions and evaluating them. So here's a simple expression language. Expressions are just values and addition. I've type-checked these ones, by the way, so we hopefully won't have the problems that we had the other day. So values and addition. So to evaluate that, we saw this the other day. It's pretty straightforward. We've got an expression where we return an integer. If we've got a value, we return x. And if we want to add sub-expressions, we'll evaluate the sub-expressions and add the result. Great. So let's do the thing we did the other day. Let's add variables. If we add variables, then two things need to happen. Firstly, we need to get the values of each variable. So we've got an environment mapping variable names to integers. And of course, that might fail. So we have some kind of, I guess we'll call them exceptions. So we'll return maybe an int to show that it might fail, and we'll use this reader monad transformer to say we also have some state that we're carrying around that we can access. So anyone not familiar with monad transformers? Do I need to say a little bit about how they work for one person? A monad in Haskell is basically a way of encapsulating some computation. Well, there's lots of ways of describing monads. In fact, how many people have written a monad tutorial? yeah, I thought there would be quite a few. So a monad, I'd like to describe it as a way of encapsulating computation. So here maybe is a computation that might fail, and reader is a computation that has some state carried around with it. So a monad transformer is just a way of wrapping one monad inside another. It's a way of having a lot of different computational effects together. And typically what you'll do if you're writing a Haskell program is you'll have a stack of these monad transformers that say we start with maybe and then we add reader on top of that and maybe we'll add more on top of that. So to write our evaluator now, to evaluate a value, we need to return something. So we need to inject something into our monad. So returning n is okay, it's just an integer. To add things, well, we'll evaluate the two sub-expressions and then we'll add the results. But we need to lift this function that we've applied into our monad because they're not pure computation, so we need to do something to turn it into to get the results of the evaluation and to push through any failure and environment that might have changed. And in the end here, all we have to do is look up the value in the environment. Get the environment, look up the value in the environment, and then return it. So it's kind of as before, except we have a little bit of plumbing to find out, to deal with these effects that we have. So there's possible failure here, and the reason we have to lift this is because lookup returns a maybe, and we actually needed something in the outer monad, the reader monad. So we have to lift it up into the monad that we're in. Here, ask, this is a function in the reader monad, so we can just use that directly. So here we don't have to lift anything. Here we do have to lift, and then here we have to return. It's fine. It works. It's a good way of managing the effects we have, but it's starting to get a little bit noisy. Now what I'm going to do is say, well, let's extend this language a little bit more. Let's have random numbers in this language. So we just add a constructor, and how do we do random numbers? Well, that's one way of doing random numbers is by having a simple way of doing it, just having a seed and then calculating a new random number from that seed and some formula. So we need to have some state to capture what the current seed is. So what do? Well, we just add another monad onto our stack, no problem. So random gen, this is a class in Haskell for different things that generate random numbers. And so now we have, rather than reader t of end maybe, we have rand t of reader t end maybe. And that means all we have to do is, everyone sort of sniggered when I said all we have to do. all we have to do is add lifts for all of the inner monads. So we have a lift here for getting the environment. We have two lifts to do the maybe computation. Of course, down here we don't need any lift at all. So there are ways of making this, having to stick lifts everywhere, slightly more or slightly less noisy. But then there's a few more problems. So here's a challenge for you. Given that we have something in ranty of readity of maybe, what happens if we have another function we want to call that is in ranty of maybe? Now that's clearly something that we should be allowed to do because we're using a subset of the effects we have. But writing this function is actually quite hard. It's completely obvious what it's supposed to do. I mean, it's just supposed to run this function and get on with it. But actually doing the plumbing to do this in general is quite tricky. Another thing you might want to do, or you might have available, you might have the same collection of effects, but somehow they're in a different order. So now let's write a function that just commutes the effects. So we have a reader and a random number generator and some possible exception. But the reader and the random number generator are in a different order. And there's clearly no relationship between these two things in this program. But this is quite a hard function to write. Clearly possible, but quite hard. So I say challenge, write the following. Please don't. It's a bit mind-bending exercise, but there are better ways of doing this. Here's one possible way we could tackle it in Idris or Haskell. I'm just switching to Idris syntax here. So we could say, well, this is annoying. I'm fed up of all this monad transformer stack because I'm pulling out too many different bits of the stack. Let's just shove everything into one gigantic monad that does everything. And actually, I don't know about you, but I often end up doing that kind of thing in Haskell. I get, lots of nodding. Yeah, it's fine. So the implementation of Idris, by the way, we'll talk about this tomorrow, but it's built on a couple of monads. We've got an elaborator monad, we've got the whole system monad, and then everything else is just thrown into that. And it's embarrassing, quite honestly, but it works. So this is the kind of thing you might do when you get fed up. You say, okay, we'll just have one evaluation monad that captures. We've got a result here, and then sorry, this is a seed. This is our state, and then this is our environment. So we've got two bits of state here, and then we've got our evaluator monad that just basically adds our possible failure in here. So we've got a function from state to maybe a new state and a value. So what we'll have to do is implement all of our stateful operations inside this eval monad. So we'll have to, we'll make it an instance of monad, so we've got do notation. We'll make it an instance of applicative, so that we've got idiom brackets. And then we can add, implement the operations that we were using before in the Haskell implementation inside the eval monad. So we can implement get and put and random number generation, and we're just implementing them inside the eval monad. So our evaluator looks a bit like this. So our evaluator looks a bit better now. So we just have the do notation, and we still have the list there. So the reason we have the list there is because lookup returns a maybe and not something in our monad. So it's a little bit less noisy in that we don't have lists on get and randint. But the problem with this one is that none of the components we've built this out of are reusable. We've had to implement get and put and random number generation. This is clearly not very good either. So it's somehow better for writing the programs, but it's not reusable at all. And we like to try to be software engineers. We like to reuse things. So this is clearly not good. Neither of these solutions is satisfying to me, and I hope they're not satisfying to you either. So composing monads gets kind of ugly and hard to manage. You can do it a little bit if you've got a couple of things in the stack, but as soon as you're commuting things, or as soon as you're working with a subset, things get quite awkward. The order matters because of how you're writing them down, but often the effects you're working with are completely independent. Now, sometimes that's not strictly true, but often they're independent. And then you're building one special purpose monad for your system is going to limit the amount of reuse you've got. So what we're going to do instead, when you're interested in embedded domain-specific languages, every problem looks like something you can solve with an embedded domain-specific language. So surprise, surprise, what I'm going to do is build an extensible embedded domain-specific language in which to capture effects and manage effects. So the rest of what I'm going to talk about today is about an EDSL implemented in Idris called effect, because, well, that's what it's all about. And I'm going to do it in 3 parts. It's all going to be, hacking again, live hacking again. Firstly, I'm just going to show you how to use them. Now, as far as you're concerned as a programmer, you may be just happy with knowing what effects are available and how to use them in your own programs. It's also going to be useful, possibly at some stage, for you to implement new effects. So, adding an effect for, managing operating system interactions, say, or getting environment variables, or looking up C functions in an external shared library and running them. As we were trying to do this morning. And then finally, I'm going to show you a bit about how the effects DSL works, so some of the internal gory details. And we'll see that there's necessary use of dependent types here to make all of this work. But to actually use it, you don't really need to know that you're using dependent types. So this is something that I generally aim for when I'm writing libraries like this, is to use dependent types to make things expressive and easy for the user, but at the expense of making it a bit harder for the library designer who has to do all the work. Right, so first let's have a look at what the types of effectful programs are. Now, these types look a little bit more scary than they actually are. So if we sort of zoom in a bit on the details, you'll maybe hopefully understand what's going on. So this M here, every effectful program ultimately has to get translated into a thing that's going to run. So it's going to get run in the context of this M. Now, the name M is suggestive of monads, isn't it? These M's don't have to be monads. They can be anything that happens to be from type to type. So one useful thing that goes from type to type is the identity function, for example. So you could perfectly well translate your effectful programs into something that runs in a pure setting just by sticking id here. So effectful programs are parameterized over a list of effects. So you give a list of effects that you want available in your type. That's what this list of effects is. And the second list of effects is, well, you're allowed to modify the set of effects that are available. And we'll see some situations where that's really useful later on. In general, the set of effects on the way in and the set of effects on the way out are going to be the same. So that means I have this shorter version that just says, okay, we have the context we're running it in, we have the list of effects, and then we have the type that the program is going to return. So to run an effectful program, we translate our effectful program into just the underlying context. I keep having to stop myself saying monad for this M, because it really doesn't have to be a monad. I guess we could call it, what could we call it? Any suggestions for a good name for that? I can't think of one. We're running it in some underlying context anyway. Right, here's some example effects, the kind of things that you might commonly see. So state is an effect that's parameterized over the type of thing you're carrying. Exceptions are effects, and they're parameterized over the exception type. So this type here might be a data structure that represents errors, say, or might just be a string for an error message. Input and output is an effect. So this standard I/O effect, that just gives you writing characters and reading characters. So we might be able to separate all the different kinds of I/O. This is something that is a bit awkward in Haskell, for example. You might want to say that, oh, I'm only allowed to do reading and writing to the console here. I don't want to be able to do network effects, or I don't want to be able to do CGI effects. But because this monad transformer stack gets unwieldy, you really don't want to separate effects in this fine-grained kind of a way. But it's fairly straightforward to do so if you're just listing the effects you have available. So file I/O is another kind of effect. This type here is what the file is open for. So remember do you remember the file language we had the other day, where we were saying you can't read from a file that's open for writing, you can't read from a file that's not open. So this type here says what state the file is currently in. Now that's one of the reasons why we might want to have different effects on the way in and different effects on the way out. It means that you can track the state of a program of a resource as you run. Question, Nicola. Type. It's parameterized over some type. Now, this type could be a unit, say. Yeah, but you're right that you could probably do something a little bit better, but given that I'm only going to allow you to construct things that are files that are open for reading, yeah, you're probably right. That probably would be better. So here's some example functions. So while that F type may look a little bit scary, this is what they look like in programs. So the type of get is just an effective program that is allowed to use the state effect, and it can do it in any context. Or raise is an effective program that happens to be allowed to use the exception effect. So that's pretty much what the functions look like. So printing a string, it's an effective program that does I/O, but the only context we're able to translate this into is I/O. So these ones can run in any context. This one has to be in an I/O setting to be able to run that effective program. Okay, so for the rest of this, I'm just going to show you a few programs and implement a few programs. So something important, there is a packaging system in Idris, a fairly basic packaging system. So to be able to get the effects package, you'll need to type -p effects, and I will probably forget to type this several times when running these programs. But it's just to pull in the effects library. Okay. So first thing is just how to use them. Here we have, here's our state effect that I just happen to have available. This is the implementation. So state is, so for now, just look at the types of these things. So state is a function from types to effects, and then we've got put. We've also got putm. This allows you to have, I guess it allows you to have dynamic types, and that you can update the type of your stateful thing. And then we have an update function that just updates the value in some state. And everyone's favorite contrived stateful program is the program, well, my favorite contrived stateful program, is the program that puts a label on every node in a tree, working left to right across the tree. Now, this is obviously quite a boring thing to write if you don't have something that manages the current label for you. So we have binary trees, some test tree here, and then label is a function that goes from trees of some A to trees of an integer paired with that A, and it's carrying a state around, which is the label, the current label. So this is going to work pretty much the same as writing this in the state monad in Haskell. The way this program looks is going to be pretty much the same. So if it's a leaf, well, we're just going to return the leaf. So F gives you do notation, idiom brackets, just like we've been using in the last lecture. F itself is not a monad, though. It's got way too many parameters for that. I don't make monads and do notation very tightly connected. Okay, so here we just return a leaf, and yes, that type checks. That's reassuring. And if we have a node, so left tree value and the right tree. So what are we going to do? We're going to label the left tree. So let's just do it the easy way. Label the left tree. Then we're going to have to read the state and write a new state. So I'll do this with get and put rather than update. So the current label, we just get that, and then we'll put a new label. And then we better do the right tree. So we better get the value for the label before we do the right tree, otherwise the ordering is going to come out wrong. And let's label the right tree, and then we return the new tree with the label paired with the actual value, and that's that. Now, unfortunately, we won't be able to run this very usefully quite yet. So what's going to happen if I do run it? Yeah, well, we need to provide a little bit more for the system to know what to do with it. So we'll have to use the run function to actually run this effect. So obviously what we'd ideally like to do is give a starting value and then have the tree label from that starting value. So we'll just do that by saying, well, we don't have any sort of underlying monad we want to run in here, so we just want to run it as a pure thing. So we'll run it as a pure thing. We'll give an initial value. Now, when you give a list of effects, you also have to give a list of associated resources for those effects. So every effect has a resource associated with it. In the case of state, obviously that's going to be the value. In the case of exceptions, well, there's no resource associated with it. In the case of random numbers, it's going to be the seed, and so on. So running a pure thing, well, and then, so we'll give it an initial value of x, and then we'll label it. So now if we try label from, let's start from 1, and it's labeled the tree for us. So you can see that I've conveniently given them names that match up. So it's worked left to right across the tree. So does that make sense for how to write that program? Because this is, if you've seen the state monad in Haskell, then I guess that's just something that's familiar to you. Now, let's make this a bit more exciting. Let's try, as well as counting, as well as labeling the tree, let's try counting how many leaves there are in the tree. So how do you think we might do that? Any suggestions? Because it's
add another state.
Add another state? Well, I was wondering if someone would suggest. I mean, what I do in Haskell. Writer monad. Yeah, so we could do that. Given that I don't happen to have implemented something that is just the writer, let's save that for later. So you suggested adding another state. Now, if you were doing this in Haskell, so if I was doing this in Haskell, I would, rather than writing a state transformer for the underlying state monad, I would probably just make this integer a pair. What I'm going to do here, I'll copy this and put it down here. So it's going to be slightly different, and I'll call it label prime. It would probably have been quicker to use some kind of editor feature to do that, wouldn't it? No, okay. My fingers would have got in a tangle. So you suggested adding another state, which makes a lot of sense. Can anyone see what might go wrong here? We've got two integer states. Which one do we mean? Yeah, what does get do? I heard someone say. What it'll actually do is it'll pick the first one. So it works through when there is some effectful function there. Internally, there is some magic, which I'll show you later, that works through the list of effects and checks which one's type check. Now, we'll somehow have to contrive only one of these type checking. And the way to do it is any effect is allowed to be labeled somehow. And it can be labeled with any type. So let's add a, what should I call it? I'll just call it LPL. The labels we have are either, it's actually a bit unhelpful to call them labels, isn't it? Either the count of leaves or the current label. Let's just call it var. Var will do. It doesn't even matter what it's called, because we're never going to refer to this again. We are going to refer to the count and the label, though. So this state is the count, 3 colons, because we've already used 1 and 2 colon. And this one is going to be the label. Now, what we're going to do is say, well, okay, this is the get on the label. So this modifier just says which label we're referring to, and then this put is going to be on this label. Now, what we're doing with the variables, with the states, is using one to count the leaves and one to label the tree. So here, we had better increase the count of labels, of leaves. So let's just do it. Let's just do it like that. So count plus plus is what we have there, effectively. So I just happen to have a main program ready that will run this. I said I got to count and label the wrong way around. So your list of starting resources has to correspond to your list of effects. This isn't going to type check because I put label first and then count. This is slightly annoying, but I can just reorder them and the program will work just the same way. Is this going to type check? I hope this type checks. Good. So what's happened here is I've run our label program with an initial environment as before, but this variant run ends is just saying I am interested in the environment that comes out after finishing this program. And then I've just pattern matched on it to say, well, let's get the number of leaves from the count. So we haven't run a program for a while, have we? Let's run a program. So that's compiling and executing, and apparently there are 6 leaves in this tree. Is that right? 1, 2, 3, 4, 5, 6. Yes, good. So, and yeah, I didn't have to put any lists or anything anyway. I just had to explicitly label each of the effects I was using. So what we've seen so far is basic effect usage. So here's state, and then slightly more advanced effect usage by disambiguating effects with labels. So I could equally have, by the way, I could have, given these string identifiers, and it really wouldn't matter. The only thing that matters is that every point where you use them, it's the same. So this would be a string too. So the only reason for these labels existing is so that the type checker can disambiguate which effect you mean. Okay. So any questions on how that works, or is that does that seem reasonably straightforward just to use?
The 2 constructors, could they just as well be in different effects?
Yeah, that'd be fine. I just find this a nice way of listing all the possible things I might be, kind of like listing all the variables you might be using in a C program, I suppose. Okay. So which one should we do next? Let's do let's do our evaluator. Oop, you see, I told you I would do this at some point. Unsurprisingly, I can't find the import if I don't tell it I want them. Right. So this is the evaluator we had before, and up at the top here, I've got a list of all the effects I say I'm going to use. So state, exceptions, input and output, and so on. And our evaluator is going to be a function that takes an expression, returns an integer, but there's a few things that might happen on the way. So there might be an exception. So I've just said, well, our errors are going to be strings. There might be a random number generation, and there is a state. This is the bit where I should have had my crib sheet with me, just in case something goes wrong. But you can shout at me if you see a type error. For a variable, well, we can just return the value of that variable. Should we use idiom brackets? Let's use idiom brackets. So variable, if we see a variable x, we'll just, yes, I meant value. I'm glad somebody at least was confused at what I was doing there. So we've got a value, we'll just return the value, and yeah, we're happy. If we've got a variable, well, what will we do? We'll need to, firstly, we'll need to get the environment. So let's do that. So all I need to do is say get, because I have state in my available effects. Then what will we do? We'll look up that name in the environment and see if it's there. So if it's not there, then we've lost. And if it is there, then we should just be able to return that value. Yeah? I hope this works. Yes. So reasonable? Yeah. So basically, here I've used the state effect. Here I've used the exception effect. So adding things, well, that should just be a case of evaluating x, evaluating y, and adding them up. And we're working in this idiom of effects. So let's just eval x and eval y, and that'll be that. Yeah. And finally, random numbers. And I can't actually remember what the function's called for random numbers. So let's have a look. Oh, I've got a lower bound and an upper bound, and that returns a number. So from 0 to n, I suppose, would do. And then let's return that. No, thank you. So this is one of the cases where stronger types, giving stronger types to your program might help. I don't know quite how to express the meaning in the types there. It's very useful having an audience to shout when you get it wrong, though. So we'll need to. I've got a little test program here that adds 42 to a random number, but we'll need a way of running it somehow. So to run the evaluator, we'll take in an environment and an expression, and it's going to return in IO just because I'm using it in an IO context later. So to run that, we'll have to give initial resources for each of these effects, so a list corresponding to these. So this is the main point where you have to think about the ordering of your effects. So exceptions don't need a resource. Random numbers will need some seeds, so let's just pick a seed. That'll do. And the state is going to be some initial state, so that'll be our environment. And then let's evaluate it. Okay, happy with that? I'm glad I'm not making type errors here because, well, you know what happens when you make type errors. You just get a big message saying it went wrong. We could even execute that, I suppose. We're running another program. Do we believe that's the answer? Well, it might be. So this is, yeah, so just... yeah, so adding 100 to 42 to a random number. Yeah. So I guess we could do a little bit of debugging here, or logging rather. It would be quite useful to know what the random number was, so we could verify it. So we could do something like, well, I'll show you the thing. In the, oh, shut up. Right. So the things we have available in the standard I/O effect are, as long as, well, given a string, do something in put string, print out string, and put string and print out string in a new line, and so on. I'll show what's going on with these handlers in a moment. So I could just say put string of. I won't be able to do this yet because I haven't said I'm going to use the I/O effect, but in a moment we'll be able to do that. Let's stick it in the middle just to show off. And obviously I'll need to add a corresponding initial resource, which in the case of I/O is nothing again. So let's try again. So 100 plus 42 plus 98 plus 100 is 240. So I think that's rather more straightforward than adding something to your monad transformer stack. That's somehow more pleasing. It's slightly annoying that you have to add these initial resources, but there's not really a sane way around that I can think of. Okay, so how are we doing for time? Yeah, I'll show you one more because I quite like this one. Yes, I know. So this is the 8 queens problem that is often used as an example of the list monad in Haskell, and so I thought, well, I wonder if non-determinism is an effect, and it turns out yes, non-determinism is an effect. So the queens, the 8 queen solver basically works by calculating whether there is a possibility of an attack between 2 positions on the chessboard, and then the solver just says, okay, I have the selection effect, and this select function just non-deterministically picks something from the thing the possible list of options. So the effect of evaluating this program is to get a depth-first search of all the possible solutions to the 8 queens thing. So again, we could compile and run this, and there's a list of solutions to. Apparently, there are 92 solutions. Yeah, well, actually, when I first, I'm glad someone knew that off the top of their head. I had a feeling somebody in the room would know it off the top of their head. When I did this, my first sanity check was Google for the solution and the number of distinct solutions to see if this program got the right answer. And I shouldn't be surprised anymore when my programs work and get the right answer, but I'm still surprised when they get the right answer. Okay, so that's how you use effects. You just basically have a list of effects that are available, and you use any function that you call must have a subset of the effects, must run on a subset of the effects you have available. So the question then is, well, how does it work? Or should I say, how do you make new effects? So I'll start with, sorry, yes.
You had on your slide this problem of, well, what about removing effects and commuting effects and so on? I guess you still have that problem with when they're unlabeled, like in...
Yeah, sure. You could.
So you do have to have some syntax, I guess, when you call a function that has a bunch of states, and you're in, currently you have 3 states around, and you call 2 states.
So
With labels.
let's see if I've understood your question correctly. Say you're in a function that has 10 states, and you're calling another function that has a subset of those states, say 5 of those states.
Maybe with the same labels or different labels.
Well, if they have different labels, then they're different effects. If they have the same labels, then fine, just call the function, and it'll work with those labels. So you can happily call any function that has a subset of effects, provided it's got to be exactly the same effect, though. So if they're labeled, it's got to be the same label. So it means that you'll be working with the same effect. If you consider labels as being variable names, it's just like working with the same global variable throughout. So effectively, we've kind of implemented global variables as a feature of the language this way, but in a nice, manageable way. I hope you believe. Does that?
You would imagine in a library that maybe a library would want to expose effect labels, or you're saying that
Maybe it would, maybe it wouldn't. I think that's up to your own software engineering mentality, I suppose. You know, you probably would want to be a bit careful about what you expose in. But I would imagine these effectful programs just being written in the context where those effects are actually necessary. I wouldn't imagine that you write your entire program in the effect sublanguage and say which ones you're using, but just when you actually need the effects that you'd start adding them. I mean, this is really what we're trying to do is have you be precise about the types of your program and be precise about the effects that your program is allowed to do. It's all about making types more precise. So another question. Yes.
It's a bit like the same question. Imagine 2 libraries exporting 2 different functions with effects.
Yeah.
Let's say a state effect on an integer and giving it the same label.
Yeah. So
you want to use them at the same time in the same program.
Well,
you would like some releveling, I guess.
Well, so this is in the tree. Yes, unsurprisingly, that didn't work. Neither did that. In this case, it's kind of why I define this as a special data type and not as a string. So this data type is part of this library now. So you will at least have some kind of scoping based on that. Yeah. So I should say, by the way, this is really new. This is something I started doing in January. So I don't have an awful lot of experience of how to use this yet. The next step, really, research-wise, is try writing programs with this, find out what goes wrong, and if these things that you mentioned as possible problems actually are problems, and then how to deal with them. So I think it's manageable, but it's something we'd have to think about a little bit. So Hannah, you had a question.
You might also want to think about polymorphism about the labels themselves. So I mean, I can imagine I want to have a state monad, or I want to have some probabilistic things which take into account the value of the state monad. I want to apply it. I want to apply that function at several points.
So there is nothing to stop you being polymorphic in your effects, certainly. So I could, as long as everything else is type correct. We are just embedding this in a language that happens to have polymorphism. So there's nothing to stop you doing anything in here that is polymorphic. And there's also nothing to stop you, by the way, having, because you can always give the compiler hints and be more precise. A fairly advanced idea I haven't really explored yet is maybe you could have relationships between things in this list. So you could maybe have parameterize your representations of locks in concurrent programs by priority and have a guarantee that you take the locks in an order that doesn't cause deadlock. That might be also the kind of thing you could do just by exploiting the host language features inside. So I think, I guess your question was, can I have polymorphic effects? And the answer is, yeah, no problem. Right, so the way effects work is you define them algebraically, and then you write a handler function that translates the algebraic data type into the thing that actually does the job. So actually, that's not where I should have started. I should have started in this file. So an effect is just, well, this very parameterized thing. It's a function from type to type to type to type. So it's useful to know what these things are. This first thing is the resource type on the way in. So remember, every effect is associated with a corresponding resource. This is something that you just need to remember throughout. There's a resource on the way in, there's a resource on the way out. So you might, in the course of applying the effect, you might change the type of that resource. Say, you're adding a thing to a vector, or you're opening a file. That changes the type of the resource. So it's useful to parameterize it over the thing going in, the thing going out. And this thing is just, it's the actual value of the computation. F, big F, is just how we refer to these resources. And this type here is the current type of the resource. This is the algebraic effect that we're working with. Every effect is associated with a handler function. Now, a handler function, at least one handler. A handler for an effect in a particular, monad or context M. So you can define multiple handlers for effects depending on what context they're running in. So you might define I/O differently depending on whether you're working in an I/O monad or if you're working in, say, a simulation of the I/O monad. So you could, unit test your I/O programs. I'll show you that in a moment. Exceptions might be handled differently if you're working in a maybe monad or if you're working in I/O. So if you're working in I/O, you probably want to print an error message. If you're working in maybe, you just want to return, well, nothing. And then we have environments corresponding to our list of effects. So this is just what we had in the interpreter the other day, where we had an environment which was a heterogeneous list of values corresponding to the vector of types. Well, here environments are just a heterogeneous list corresponding to the current type of the resource for each effect. So this environment is something that you feed in to initialize the evaluation process, and that's the only time you'll ever actually need to know anything about the environment. So to define a new effect, what you have to do is implement a data type of this form, and we need to write some handlers that actually process the effect. So state is pretty much the simplest one you could hope for. So state is an effect where getting something with a resource type on the way in of A, resource type on the way out of A, will return something of type A. And then putting something, into some global state, given some value of type B, well, the resource type on the way in doesn't really matter because we're replacing it. The resource type on the way out is going to be this B. So put is just allowing us to, this isn't necessarily a good idea, but put is now allowing us to change the type of things as we go if we really want to. Situation where you might want that, again, is where you have some dependent type as your state. So you might say that we have a vector that's growing, so we need to be able to change the type. So to handle this, we have to write a handler function. Now, the handler function is slightly complicated because of this continuation passing style it's written in. So first argument is the resource, so that's the state. Second argument is the effect, and then K is what we do next with the when we finish processing the effect. In this case, with get, well, we just feed the current resource through. So we just pass the state and the return value through to the continuation. And then putting, well, we're updating the resource with n. So, happy with that? Is that a reasonable thing? So you might have a question of why we're using continuation passing style here. The reason I'm using continuation passing, well, two reasons. Firstly, because I find it when we're working with essentially two return values, because you're returning the environment and you're returning the value you're working with. I find it much easier to work in continuation passing style in that context, because the continuations have two arguments. But there's actually a more important reason, which is sometimes you won't want to run that continuation. And you need to have some way of indicating that. So an example of that, let's have a look at how the exception effect works. Well, exceptions, all you can really do with exceptions is raise them with some value. So exceptions don't have, their resource type is just nothing. So and when you raise an exception, well, that'll return, well, the exceptions of type A won't return anything, and, well, actually, it can return any type because we're not going to continue running, so it doesn't really matter. So to handle an exception, say we're in a maybe context and an exception happens, so the F language needs to find out how to handle that effect in maybe context. Well, we're not going to do anything because we've thrown an exception. So the reason for having a continuation, really, is that you might actually not use it, or you might use it more than once. So that non-determinism effect we saw earlier, actually you're running the continuation once for everything in the list that you gave. So it gives you a bit more flexibility to have a continuation there. So the way to implement effects, therefore, all you really need to know is you have to write down the effect algebraically, and you have to write down how to run that effect in different kinds of contexts. So this example here, so exceptions might happen in maybe context, they might happen in I.O. So in I.O., it's it prints it and then exits the program. The reason for this, believe me, by the way, this is a function that exists in the library. It's essentially it's unsafe coerce, and this is just because it's kind of annoying to come up with a value here. I can't persuade the type checker that the value that the exit returns is the value I want. And to be honest, it doesn't really matter because the program is given up anyway. So I thought it was okay to trick the type checker there. And I have another version of I/O exception, of an I/O monad that allows you to throw exceptions and handle them. So this is I/O except. So I've got three different ways of running this exception handler. The Queen's solver, the Queen's problem solver, by the way, was written in this way. So the only effect available there is selection. So select something from a list. So in maybe context, it returns the first answer it finds. In list context, it returns all the possible answers it finds. So we have a couple of different ways of running it. And you'll see here that we're basically running the continuation once for everything in the list. So you can't necessarily combine effects just because you have them. You have to have some a handler implemented for every effect in the context you want to run in, which because you have to explain somehow how to run these programs. Effectful programs are really just descriptions of the program you'll run when you get around to running it, and these handlers tell you exactly what to do when you do get around to running it. Okay, one more program I'll show you. Actually, no, I'll show you two more programs before I show you briefly how the effects language works. The other day I showed you oh, for goodness sake. I might just make it a default thing to include, and then this will never happen again. This is a program that oh, this is just gratuitous use of labeling. There's not really any need for that here. This, if you remember the other day, we had a description of a file management protocol where you could only read a file after you opened it, and you had to close the file before you were done. So done the same thing here, but using effects. Now the file effect, we're really using the fact that you can change resource types here. So there's five things we can do with files. We can open them, we can close them, we can read, write, and we can check for end of file. So to open a file, the resource we have when we open a file must be empty. We're not allowed to open a file if we already have a file there. And when we've opened it, the resource is a file that's opened. And we can only close a file if the file is open. So the fact that the effect is associated with a resource means that, well, what's the resource going to be in this case? It's going to be the file handle. And if you want to have multiple files, well, just have multiple effects, each of them referring to a particular file. In fact, if you want to have a list of files, then just pass that in as a list of effects. So we can ensure that opening, reading a file works according to the file access protocol just by writing it down as an effect and writing handlers that work properly with those effects. I've got two handlers for this one bad and one good. This is a bad one. In I.O. world, we just assume that opening the file worked, which is clearly a little bit dangerous. So I I might change this IO with exceptions monad to be the default IO. That might be a bit neater. So in this case, when we open the file, we check that it works. Now, if something might fail, if you're throwing exceptions, it's quite useful to be able to catch them as well inside your program. What we have in the effect language is a catch construct that says, well, anything that is possibly an exception can also be caught, so like maybe or IO except. So this example file program, so we try opening the file, reading it, printing the contents, getting the number of lines, and then displaying it. And if that fails, then we use this catch function just to catch the exception that might have been thrown. So catch is just a primitive in the effects language that allows you to manage any possible failure that could happen with your effectful programs. So this is just like it's pretty much like the program we had the other day that it won't type check if we forget to close the file, that kind of thing. No. Yes. Right. There's a noticeable pause there. So we're starting to work it quite hard. So there's quite some work going on to type check that. Right. And the other program I wanted to show you is an I/O program that I'm not actually running as I/O. So -p effects. Yes, I remember that time. So this is your basic I/O program, and this will run in any context provided I've defined an I/O handler for it. So it's it's a standard what is your name program. So there we go. That's pretty much what you'd expect. But I've also defined a function. This is in the I/O library called make_strfun. It turns an I/O program into a program that takes a list of strings as an input and gives the thing it's going to do and a list of outputs. So this is effectively a way of running I/O programs in some pure way. So I can say, well, when we run this program, we'll give it the input of my name, and then the output will be the list of things that program will print given these inputs. I'll use show so you can actually read that more easily. What? No, you can't show that, can you? Okay, fair enough. Okay. We don't have a show instance for the empty tuple, apparently, so I can't do that. That's slightly surprising, actually. I could define one, but let's not do that. So this allows us to possibly even reason about I/O programs. I haven't tried doing this, but it might be possible to write proofs of I/O programs just by having proofs of what happens when you run them in this list style handler. So yeah, this is the handler for how you deal with lists. So basically, it's pulling something off the list and then adding things to the output list. So it's a little bit ugly there. Probably could be made a bit neater, but okay. Okay, so the last thing is just to give you a little idea of how this effects language works, and it's maybe better to look at this offline, but I'll give you some pointers as to what's going on. So at the top here, we've got how to define effects, but there's a little bit of magic necessary to deal with checking whether we have the right effects available to carry on with the program and translating those algebraic style effects into actual functions. So a couple of things we're going to need. We're going to need to generate proofs of list membership and lists being sublists of another list. So this predicate here, sublist, is a predicate that says whether this list is a sublist of this list. And, well, the empty list is obviously a sublist of the empty list. That's easy. And you'll either, for every element in the list, you'll either keep it or you'll drop it. So a proof just says whether the thing is still there or whether it's gone. So to construct a proof of, I don't know, 1 is a list, is a sublist of the list 0, 1, 2, that'll be drop of keep of drop of sub nil. So we're just going through the list saying what's there. We'll also need to know whether an effect is an element of a list. So I could have done this in a slightly more polymorphic way, I guess, but it was easier to do it this way. So saying whether an effect is in a list of effects so an algebraic effect is in a list of effects. It's either here, it's either the first thing, or it's later in the list. So this is just like the element proofs we had before, but it's specialized to this particular problem of effects. So the effect language, that's what we have. So we have a way of making values. We have a way of binding. So this is how we get the do notation, injecting values and binding things. This effect constructor here, this converts some algebraic effect, that's this thing, into an effect program. So the proof here says that yes, that effect is one of the ones we have available, so you're allowed to use it. And then this little bit of magic here is just updating the type of if that effect changes the type of a resource, then this function is just basically changing it in the list of effects on the way out. Also, this lift function. Remember, the Haskell monad transformer programs are full of lifts. Well, we can't really get away without lift. What lift does is, given some proof that we have that the function we're calling has a sublist of the effects we want, we can run it. And then this function here is just going to update the result. So using the proof is actually computationally useful. We're using that proof to pull out the effects resources that we have, and then we're using it again to put them back in the outermost thing. And then we have a couple of helpful things and a labeling thing. Now, you can see just at the bottom a telltale hint of what's coming next. So you haven't seen lift in any of our programs. The reason you haven't seen lift, and you haven't seen any of these proofs in any of our programs, the reason you haven't seen lift is that I actually have a little magic implicit function that does the lifting. So if the type checker finds something where you're calling a function that doesn't have the effects, the exact effects, then it will implicitly insert a lift that does that work for you. And this notation here, this says, well, I need a proof that y is a sublist of x's, but I really don't want the programmer to have to provide that. So this little annotation here says, whenever you get to this function, this is how you automatically construct the proof of the sublist. 100 here, by the way, is a maximum search depth. So this is pretty dumb at the moment. It just does a brute force construction of the proof until it works. So I have very limited tactic construction features in Idris, which I implemented specially to get this working. Hopefully one day, I have a student working on it. Hopefully this will get a lot better in future. So this find sublist is defined up top here. Where is it? Let's find sublist. So given the search depth, it constructs a tactic. So remember the tactic style proofs. Well, the tactic style proofs can also be written as a data structure and then invoked using the reflect tactic. So this is just, well, you can see it's just brute force, trying every possibility. Okay, so that's effects. That's how they work. And I have in the library I've defined a few effects. So exceptions, IO, state. Non-determinism. But there's clearly lots more effects that we could usefully define. One of the exercises, in fact, is to define a couple more effects. So I think one nice thing about having effects done like this is that you can separate a lot of the I/O style effects from each other. So we can keep network effects separate, file effects separate, graphics effects separate, and just be more precise about what our programs are supposed to do. Okay, so that's all I have to say about effects. If you have any suggestions or comments on how it might work, how it might be improved, then that would be great, because I say this is very new stuff, and it's pretty much the first time I've presented it in this form. So any comments you have, I'd love to hear it. Okay, I think we should stop there. Thank you.